So before we begin, I brought some images, photos of the first something. In 1832, what you see here, it's the first computer or first mechanical computer that was able to do several calculations. Back in 1946, what you can see here is the first electronic computer. During these days, one computer had to fill up all the room, and if there has some kind of small malfunctioning problem in the computer, you had to change bulbs or resistors in the hole, or to find out where exactly is the problem and then change those physical components. However, in 1947, there was a big first that changed the way electronic devices are being made, and this was done at the Bell company's laboratories, where it was first shown by Cvd that the way to connect two different materials or semiconducting materials, and together to perform a specific function. And what you can see here is the first transistor that was developed by Cvd and in the Bell laboratories. Now we will see how this kind of advancement established eventually the field of lab on a chip. And this kind of invention resulted the Nobel Prize even. So today we're going to learn about how we can actually do this kind of sculpturing or patterning, these kind of very nice, very unique, beautiful structures at the micro and nanoscale. So welcome to the last lecture in the course. And today we're gonna, after we had learned about system level and about specific theoretical, physical and chemical reaction on designing the lab on a chip, now we're gonna learn about how you can make or fabricate or manufacture the lab on a chip. So the goal of Unit 8 is first to identify different approaches or techniques for micro and nano fabrication, to design a basic microfabrication process. We want also to describe different techniques that allows material additive techniques to add materials on surface of substrates, and subtractive to remove them. So if you remember, on our first lecture, we discussed what are MEMS. And MEMS are microelectromechanical systems. Second, let's do laser pointer. Microelectromechanical systems. They integrate microtechnology, microfabrication, nanotechnology, and microsystems. And I show very nice photos of some fabricated or manufactured microscale and nanoscale devices. And these kind of devices enable, sorry about it. And these kind of devices show the ability to have different novel functionalities, such as high throughput analysis, or developing micro devices that can be weared, such as the interocular pressure devices. But these are all very, very nice pictures, and I agree. I mean, I'm very much excited to show them. But how do you actually build those devices? How do you go into the lab or go to some room? What tools do you use? And how do you actually make those kind of devices? So this is what you're going to learn today. And as I said, everything began 70 years ago, when almost 70 years ago, with the discovery of the semiconductor industry. And it's all related to transistors, eventually. And if we look at transistor, how it actually evolved since this kind of discovery, there is the Moore's law showing that the number of transistors is a function of the year, and we see the development of how many transistors per chip or per processor there are, and we see the number is doubles every 1.5 to 2 years. The market for the semiconductor industry or development transistors or electronic devices just multiplies and increases every year. And there's also some field also in China. Now, when we look at the structure for microchip or microchip semiconductor, we see layers. So the whole structure is based on layers. So we have a silicon substrate or kind of a substrate, different materials, substrate. On top of it, there's the active device layer that is conductive, and on top of it, there is the interconnect network that connects between the active device layer. And here you can see a very nice photo of how the microchip looks like, and it's based on connection where the devices are not connected one next to each other, but they are connected vertically. So we have one device, another device, another device, everything by layers. They're connected vertically. Here is an inside image or a microelectronic image of a transistor. And what we can see here is that we have the transistor is a kind of a side view, and we have some kind of silicon material here. And we have another material that coats it, and another material that fills the gaps. So everything like from the side view. And together with this kind of materials, a transistor is fabricated where you have the gate is this kind of distance. You apply currents between two different points, and you apply voltage difference across a gate. So all this kind of development, and this is not a course about microelectronics production or fabrication methods, it's about lab-on-a-chip microfabrication methods. And the reason I show you all this kind of development is that you can actually, so these kind of tools that were developed for the semiconductor industry to manufacture processors and transistors and so forth, we as the lab-on-a-chip scientists are able to utilize this kind of techniques as a way to make or manufacture our own lab-on-a-chip devices. And this is the goal of this lecture, is to get familiarized with these kind of techniques and use them, and learn how you can use them to build the lab-on-a-chip. So there are two ways basically to build a house. So if you look at some kind of small model, there is the top-down approach, which means that you take a big chunk and you start carve your structure inside this kind of bulk material. And there is the bottom-up approach that takes building blocks together, connect them together, and from that you build your structure. So any questions so far, or also on this slide of a top-down, bottom-up approaches? Okay. So what are the tools? In this field called micro manufacturing, because you use the tools to manufacture microscale structures. And usually it has this kind of list of different types of techniques. Usually we use, we have a kind of a surface or a substrate that on top of it, we do all the fabrication. We can use this kind of technique called oxidation, thin film deposition, photolithography, all those kind of techniques we're gonna learn soon. There are actually every kind of university or institute has their own place to manufacture these devices. MIT, Stanley National Labs, I'm sure also in China. In these kind of labs called microsystem technology labs, where these kind of facilities are present in a clean room. So it's a room that has a lot of filters that are defined by different classes. Class 10, class 100, plus 1000, we're going to see how it looks like. There are also one at the Ben-Gurion University, Nano-Fabrication Center, different clean rooms. We call them Fab 1, Fab 2, Fab 3, different classes. The smaller the number, the cleaner the air. And everyone are kind of dressed, cleaned. You don't want to introduce any particles from outside to the clean area where you manufacture the device. And the reason for that is that if you provide some particles that are more or less at the size of your device, they can damage the device. So you want to have it in a very clean area. Now, what are these kind of classes? Classes, we have 1 until 100,000 and more. But basically what it tells that, for example, class 100, meaning that you have a maximum number of 100 particles that are smaller than half a micron in a per cubic foot of air. So it's a very, very clean environment, and you have some kind of sensors that detect how many particles you have. And usually a good cleaning place, a good cleaning level, class for lab-on-a device is usually around 10 or 100. While very much for microprocessor, you talk about class 1, that, for example, you have an Intel or other companies. When you have one or less particles per that are smaller than half a micron per cubic foot, which is a count on like a cubic meter. So it's very, very, very clean area. Do you have any questions so far on those two different slides? Okay. Now, after we go inside the clean room, and usually in my class, I have like a field trip inside the clean room, but we cannot do that. I think it's the best way is actually go there and see how it goes. So for how we actually utilize or how we manufacture these kind of structures, such as microfluidics or electrochemical electrodes, for that we have this kind of overview scheme. And the first part that we do usually, we take a substrate. It's called a wafer. We're going to see soon what are those kind of wafers. We put some material on top of it, a material that is responsive to light. We get a pattern from the light. We shine light with a pattern that transfers to this kind of material. And then we remove some of the material that wasn't exposed or didn't had any interaction with the light. So this kind of way of putting this kind of photosensitive material, shining light with some kind of features that are transferred to the material and removing some of the material, this kind of step done by step by step by step, And that way you can get this kind of features onto your device. Then usually you have testing of the device on the wafer, on the whole wafer itself. You have multiple devices. You can use a saw to dice your wafer into multiple chips, and then you have an individual die, it's called. You can connect it, assemble it, test it, and so forth. So let's see. Okay, so let's see how we are doing that. So the first step that we need, and I'm going to do step by step, kind of like this kind of how we can make this kind of cantilever on the substrate. And the first step is to choose the substrate that you're going to use. And this is our wafer, that on top of it, we're going to deposit some materials. But there are different types of substrates. The most common one is the silicon wafer. These are silicon substrate that are basically done from molten silicon, that are then molten into a big cylinder like this, and then are being diced for substrates. And the whole process is done on this kind of substrate. And you have different sizes, different diameters, and so forth. Silicon wafers are very good material. Obviously, silicon is a semiconducting material. However, there are also other types of materials such as steel or aluminum. And usually, all of them have some pros and cons, but and it's based on the experience or the goal of your device. And when I mean device, I mean the lab on a chip device. But the most common one is silicon. The good thing about silicon is that by doping, or basically inserting or tunneling some different types of ions, such as boron, phosphorus, arsenic, antimony, into the structure of the silicon, what do you cause is a contamination. And it's not a bad contamination, it's good contamination that affects the resistivity of the silicon. And then it's called a semiconductor because depends on the temperature. You can transform it from an insulating material, you can heat it up into a conductor. That's why it's called semiconductor. Now there are other substrates that we can make our device. We can use glass wafers, plastic, PDMS. PDMS is polydimethyl siloxane. It's the material that we usually use to manufacture microfluidics. I'll show it, I think, at the end of the lecture. Titanium, sapphire, and so forth. But eventually, these are different substrates that on top of it, we're going to do all the process. So any questions so far about choosing the substrate or the process? Okay. So we chose the substrate. And now comes the step of depositing the material. Now, I don't know if all of you remember, but before we had the digital cameras, with CCD cameras that we were taking a picture and saving that on a file, there were the old cameras using a film. And a film, it's kind of like a paper, like a material that whenever it's being exposed to light, the image is being carved on this kind of material. And then, in cameras, you were going inside the room that was kind of dark with red color, and you were developing the image. The same process is done with microfabrication. they deposit this kind of material, okay, that eventually will be exposed to some kind of external light, and will transfer the image from the external light into the device. So this kind of process called deposition of materials, and we have, and we will come back soon. But in order, so we have this kind of material that it's responsive to light. And now see how we can do the transfer. And this kind of transfer of the features of how the channels, for example, looks like, it's called lithography. Or specifically, when you use light, it's called photolithography. It's like shining light with different structures. So you just transform the structure onto this kind of photosensitive material. Now, this kind of process called photolithography. Lithography is by carving photo by using light. And this kind of material that is responsive to the light called photoresist. So first we have the wafer, silicon wafer, and we need to cover it with homogeneous film layer of the photoresist. That later on we can shine light on it and transform the image. So for that we have recipes. It's actually like exactly like recipes, you know, like you make a cake, or if you want to get a 7-micron thick photoresist, for example, you place it on a spinner, it spins to dispense the photoresist. You spin it on 3,500 rounds per minute. You put it in the oven, 90 degrees, 60 minutes, take it out, expose light, and then put it in the developer solution, and then put it again in the oven. It's really like making a bake. That's why it's also called a recipe. So we have this kind of photoresist that you have a dispenser, and it dispenses and covers homogeneously the whole substrate with a specific thickness, depends on the recipe that we use. And then the next step is to expose the light, expose it to light. So in red, we have the photoresist on the substrate, which could be silicon. And to expose the light in a specific structure, we have a thing called mask. And this is the mask. The mask has areas that light cannot shine through, they are opaque. And there are areas that the light can go through that. And then only this area, depends on the mask, is being exposed to the light. Any questions on the mask and the photoresist? Is it clear? So let me repeat it again. So you have the light. The light only go through the areas that are open, or they are not opaque, they are transparent, and then they interact with the photoresist. Now the photoresist is a kind of a polymer that whenever light touches it, it responds. Now, whenever the the light touches, in this kind of resist, what happens is that the chemical interactions between the polymers are being loosened, they're being weaker. So whenever the light touches, the connection between the polymers will be weaker. And then when we put in solution that develops the photoresist, only this area will be removed. And this area that doesn't touch the light will stay. This kind of photoresist is called positive photoresist, while there's another type called negative photoresist that whenever the light touches, the opposite reaction happens. It actually, the interaction chemical connection actually start to, they are harden, become stronger. And because the light touched here, now when we're gonna develop it, this is gonna stay. You know, the other ones will be removed. So let's repeat it. We have two types of photoresist. We have a positive photoresist. We have a negative photoresist. Positive means that the light shines through the mask. And whenever they touch the photoresist, this kind of photoresist, the bonds will be destroyed. And when we put it in the solution that develops, this area will be removed. And the other area will stay. And for the negative photoresist, where the light touches the bond, there's a cross-linking between the bonds, and this area will stay after development. Okay, any questions so far? Now, the next step for us will be that, as I told you, like we do that in layers. So if now, for example, if we have this kind of structure through the mask and we are in this step, and think about it that now, instead of putting photoresist on all the wafer, we are evaporating or sputtering, putting some kind of layer of gold. Gold will be on top of all this kind of area, right? Because deposit gold on all over the wafer. But then when we put it in another solution, now a different solution, it will remove the photoresist, these parts. And what we get, what we end up is only with this kind of structure of gold. So think about it like as an electrode. We defined the feature, how the electrode look like. We did this kind of processes, steps, and eventually we came up with a small area that has gold on it. Again, no, sorry. We first deposit, I guess the next step is depositing on all over the surface, very thin layer of gold. Okay, sorry. Sorry, we have very thin layer of gold on everywhere. And now, because of, we put it in another solution that removes the photoresist that was not removed before, this area will be removed together with the gold. Same as here. So what we came up with is, sorry, it's a very thin layer of a gold electrode, gold contact. This is the way that we fabricate different structures, or we can translate different features or dimensions of our device. So any questions so far? Okay. Thank you. Now I need to get rid of that somehow. Okay. Every photoresist has its own data sheet. And for that, it's exactly kind of a recipe. And here it's a kind of a data sheet of a photoresist named SU8 2000 from a company called Microchem. And this kind of photoresist is known to be very, very good to make these kind of structures that are very, very, very high and very thin. So each photoresist, when you start to design your fabrication process, you have this kind of data sheet, you go online. You have process flow. So for example, here, first you take the substrate, the silicone, you do pre-treat, then you coat it with the photoresist like we saw with the dispenser. There is some step called the edge bead removal, but I'm going to focus on, there is kind of like a heating phase, exposing to the light through the mask. Then there's another process that's called post-exposure back. It's kind of to make the connection stronger, and developing and rinsing and drying. It's the same thing as we saw in the previous slide on the steps of putting the photoresist, shining the light, and removing the photoresist. You have, actually there are different, I don't know if you see, but there are different models or of SUA. There is 2025, 2035, usually the number of the 25 or 35, meaning that the optimal thickness of the photoresist. The 2035 has a more thicker optimal thickness than the 2025. And there is this kind of figures that shows the optimization. Like, for example, if you're going to use 2035, which is this one, and you want to get 60 micron thickness, then what we need to do is to spin it for 2000 rounds per minute. Or if you want to get around 40 micron thickness, we need to do that in 30,000 rounds per minute. So there is kind of like a guidelines how to build your recipe. Like, okay, I want to have 40 micron thick photoresist. It's meaning that I need to spin it for 2000 RPM, and that's for 30 seconds usually. Then there is the part of like the exposure. It depends on the thickness. This is how much energy, which means how much time we need to expose the photoresist. Some need to 5 seconds, some need 30 seconds. And then there is the heat, how much time to heat it, and so forth. So from that, you can actually build your recipe from all this kind of data sheet. Any questions on the data sheet? Okay, thank you. Now I talked a bit about photomasks, but here we look more in depth what is a photomask. And here are the features that we design. Usually we draw that with a CAD software such as AutoCAD or other software. And we send for manufacturing. And we have two main categories of photomask. There is the light field, meaning that most of the surface of the mask is transparent, and only the features that you want to transform into the photoresist are black. Or there is the dark field that you have, most of the areas are dark, so light cannot go through, and only the features that you want are transparent. So we have a light field and a dark field type of masks. And that was how we able to pattern the features or this kind of features that we want onto the substrate itself. So there are also ways, I mean, eventually, when we shine the light, we are bounded into the into the into the wavelengths of the light. Specifically, the most used one is ultraviolet, UV. So we cannot make features or pattern features which are smaller than the wavelengths. So how can we do features? How can we pattern features which are smaller than the UV wavelengths? For example, here, there were patterned holes with 80 nanometer diameter. And from that, we move out of the photolithography and we are going down to the electron beam lithography. So instead of photons, the shine light interacts with the photoresist, we have electrons that are being exposed, that they interact with some kind of material called a resist, not a photoresist, because it's not reacted to light, it reacts to electrons. So we pattern the same way like photolithography, just pattern with the electron beam lithography. So the same process, we have a substrate, we spin on a resist that responds to electrons, we shine a very straight and coherent beam of electron, and the areas that interact with the electrons will later on can be removed during the development. So that's how we can actually pattern features which are at the nanoscale. And the higher the exposure amount that we expose our photoresist, it will also control here, for example, the amount of resist that will be left during the development. So this is for a low amount of 2.0 nanocoulomb, because electrons have charge per centimeter. We have this kind of features, bigger features for the resist. When we go up to 7 nanocoulomb per centimeter, about almost more than 3 times higher yield exposure, we get a much smaller sizes of the photoresist, of the resist, because more resist interact with the electrons and later on can be removed. Any questions on electron beam lithography? So other ways to pattern nanoscaled features, there is also the nano printing using soft lithography because we have making this kind of a stamp that, like a stamp, it touches the material that we want to deposit, take it, and then put it on the substrate and pattern this kind of printing, this kind of material. And with that, you can make stamps that has the size of a nanoscale and can pattern features that are in the nanoscale. Other ways to pattern nanoscale features, there is the nanoprinting using the SPM, scanning probe microscopy. It's called the deep pen lithography. And it's actually using like an AFM. It's using the tip of the AFM to, while putting some kind of molecules on the edge of the tip, and with that you can just deposit single molecules on the surface of your substrate, because the tip of the FM tip, the probe itself, can go down into the nanoscale edge. So it can put single molecule one by one and make a thing called self-assembly monolayer. Okay, any questions so far on ways, kind of like ways to do lithography? e-beam lithography, nano printing, and so forth. Okay, thank you. So I'm going now a bit back, one step back, because I wanted you, or not exactly back, but I wanted to first learn about the substrate, then about how you can do lithography to transfer the pattern. And now I'm going to talk with you about how we can deposit different types of materials, such as the gold layer, different types of materials that are not resist. And then how, whenever you put, for example, the layer of the gold, then how we can remove or cause the material to be removed from the substrate in specific areas. This will be the removal of the material. So there are different techniques to do that. And we divide these two techniques into the additive techniques that put material on our demand, and subtractive is that are removing material on our demand. So additive, we have casting, molding, oxidation, deposition. There's physical deposition of the material, or there's also chemical reaction that cause the deposition of material, and the spin-on, the one we saw before for the photoresist, spinning the material. For subtractive, we have machining, grinding, and etching. Etching is removing the material by using wet solutions or even with dry, under dry conditions. And these kind of techniques that I showed here inside the rectangle are the techniques that we use to build our bio-MEMS or lab-on-a-chip devices. So let's go down and see, let's go and see what does it mean. So first, we want to define properties or characteristics that define our coatings of the material. And for that, we define two different variables. We have the thickness, okay, of the deposited film for the vertical direction, and the thickness for the horizontal direction. And now, if we have the same thickness, T, D, the vertical is more or less like the horizontal, then we have a conformal and uniform coating. So it's uniform, it has the same thickness, and it's conformal, the same thickness everywhere. However, when we have the thickness from the vertical area is thicker than the horizontal, we have a non-conformal coating. And when we don't have any kind of similar coating, even either on the horizontal or the vertical, what we have is non-uniform coating. So always first we need to define what kind of coatings we have. We look at the cross-section and we says it's either conformal and uniform, or non-conformal or non-uniform. Questions on this slide? Okay. So we have the spin coating that we use for the resist. And for that, there is, this is a side view, like when you put the photoresist, we start to spin it, it being dispersed equally on the substrate, and then you get a very thin layer of the photoresist. Now there is the equation that describe the thickness of the resulting film as a function of the initial concentration of the polymers that we put in the solution, but also the angular rotational velocity the viscosity of the material, and also there is some kind of proportional constant for each photoresist or spinner by itself. It's a different value. So what you can see basically that if you're going to spin it much faster, we're going to have thinner layers, or if we have more viscous material, then we have more thicker layer. Now that was used for polymers coatings. However, there are other materials that we want to deposit on the surface of our substrates. For example, we want to deposit oxygen on silicon wafer that will perform an silicon oxide SiO2 layer. And the reason for that is the silicon O2, which basically it's glass, it's silica glass. It has insulating properties, while silicon is a semiconductor. So usually when you build a transistor, by the way, you have a very thin layer of oxide, silicon oxide, which is your gate. And it is not conductive. So that's why we want to have another way to deposit oxygen. Usually when you expose native silicon just to air, you have something called native oxide layer, a very thin layer of 1 or 2 nanometers of oxide. Always you have it. But here we're talking about much thicker thicknesses of layers of oxide. And the way to do that, we have 2 different ways. There's the dry oxidation, which basically we are flowing oxygen on the surface of the silicon wafer at very high pressure, and gradually the oxide layer increasing. Or we have the steam oxidation. We put silicon with water, again, 3 hours, 1000 Celsius degrees, and we get the silicon oxide that we want to. Any questions on thermal oxidation? Also here, there are models describing the oxidation rate. Okay, how fast the thickness is growing for the oxide. Very nicely was done by Dell and Groove back in 1960s. And here are the parameters. You can look into it and design your own process, how much time you need, and what is the concentration of the oxidant that you need in order to have a specific rate, oxidation rate of your oxide. Okay. Now there are 2 main ways. I talk about the oxidation and the spin-on, but there are 2 main deposition categories that are based either by physically putting the material on the substrate, or by exposing the substrate into chemicals that cause a chemical reaction on the surface and therefore has depositing another material. So we're going to go over the physical category, and these are physical vapor deposition, meaning that we have a vapor and we take the material, solid material, we vaporize it very high in temperature, and all the molecules that are vapors in a gas phase, we put them on the substrate over there, and then they're being deposited physically on the substrate where we put them. A very common technique is evaporation, sputtering, laser ablation, and even hybrid methods. So we're going to go over the 2 first options. For thermal evaporation, we have a crucible, which is kind of like a chunk of the metal itself, of the material itself, for example, a chunk of gold. And what happens is that we apply a very high current flowing through this kind of crucible to the material, causing the material to heat and to start to evaporate, to the metal ions to start to be in a gas phase. There's also an option to cause this kind of evaporation by applying a very strong electromagnetic field that will cause electrons to hit the crucible and in a very high velocity cause the transfer of energy will cause the metal to go into a vapor phase. And then the vapored phase of the metal, such as vapors of gold, are being transferred towards the wafer itself. So we have here two wafers, one here and one here, and the material gradually deposits on the surface, physically deposit on the surface of the wafer itself. So this is the way that we use to evaporate metals such as gold and make a very thin coating of the metal layer on the surface of our substrate, for example, for the electrode fabrication. Any questions on thermal evaporation? Okay. Another way to deposit metal, physically deposit the atoms, is using sputtering. Now, sputtering is a bit different than evaporation because what we do is we apply a very strong, very strong and energetic ions on the surface of our metal, of the substrate, causing to the atoms of the metal to kind of like splash, like sputtered on the surface of our wafer. So we don't actually evaporate them, we kind of sputter them on the surface of the wafer. And this is done by heating gas, usually inert gas, into plasma, and then applying a specific electrical field on the plasma that causing the ions in the plasma to run very, very fast very, very fast up to the target, to the metal material, causing sputtering back on the wafer itself. So we have a sputtering rate that's described by the S, and also it depends on the ion current density, the atomic mass of the materials, and as far as the sputtering yield, which depends on each type of metal. Any questions on sputtering? When we compare evaporation versus sputtering deposition, sorry, we can see that evaporation gives us a very conformal coating, right? Remember, we have this kind of uniform, non-conformal but uniform coating, because it's very much towards the same directions when you do the evaporation of the atoms. While sputtering gives you a more conformal, although it's still non-conformal coating or non-uniform, because of the directions of the atom towards every direction and not in a coherent way. In evaporation, we need a kind of a low energy to heat the crucible and to cause the atom to evaporate, while for the sputtering we need a very high density. Usually the deposition is more porous, while sputtering is more denser. There's a poor adhesion for the gold or the metals versus better adhesion. And basically we have a poor step coverage when we use the evaporation than with the sputtering. Okay, so these were kind of the main physical ways to deposit metals on our surface of the substrate. Do you have any questions on physical deposition or physical vapor deposition? We call it PVD. Okay, so let's move into the chemical vapor deposition, CVD. And in CVD, we are depositing a material on the surface of the substrate, but not because of physical movement there, but because of chemical reaction. Main CVD methods are divided into three. We have the low pressure chemical vapor deposition that we don't need, we need a very low pressure to do that, or plasma enhanced CVD. And the third one is the atomic layer deposition, ALD. All are names for different techniques, different tools. And usually it happens inside a furnace, like an oven, and you put the wafers, you put multiple wafers, one by the other, together, and put them inside the furnace. It can go up and usually under gas flow, because you want to introduce the gas that will react chemically with the surface of the substrate to cause the layer. So we have a gas inlet and gas outlet through the pump. And usually this kind of furnaces get into 1,000 or 1,200 Celsius degrees, very, very high temperature. Now, it depends on the kind of the layer that we want to have. We need to design the CVD reaction, the chemical reaction. So for example, if we want to actually coat a specific material with silicon, we don't have a substrate for silicon, we have a substrate from another material, we want to coat it with silicon, we can flow a precursor, it's called, the gas precursors, of hydrates to coat from silicon H4 into silicon plus 2 moles of hydrogen gas. And it's been done between 600 to 1,150 degrees. So we flow this kind of gas and cause the reaction. Or we can use another options like synthesizing specific gases, or 2 or more gases that cause the reaction and, for example, causes gallium arsenide. It's another type of semiconductor on the surface of our substrate. So it's a chemical reaction and not a physical reaction. It's a chemical reaction, depends on the precursors or the gases that we introduce to the wafers in the furnace. Any questions so far on chemical vapor deposition? Okay, thanks. So the first example is the low pressure CVD. And the good thing with the low pressure CVD is that we don't need a high pressure to make the process. So we need a kind of subatmospheric pressure, which actually helps to reduce some kind of undesirable chemical reactions and have a very more homogeneous film, uniform film on the wafer. But it requires very high temperatures, usually over 800 Celsius. So example for this kind of reactions, usually for polysilicon, silicon nitride, low temperature oxide, or even diamond films. We can make diamonds from carbon. But it's not relevant to if you want to make any metal, substrate with metal or polymeric films. So that's a low pressure CVD. The plasma enhanced CVD, chemical vapor deposition, which called PE CVD, is that now we introduce the energy not through temperature, but through a plasma source. Okay, plasma is a gas that has an inlet, and the gas is heated and becomes a plasma. And the plasma is being flown towards the wafer where it's being deposited. So we can actually come up with a much higher or much faster deposition rates, 10 to nanometers per minute. So if you want to have a very fast coating, we can use the PCVD, and we also can use low operation temperatures between 200 to 400 Celsius, even sometimes at room temperature. However, the downside is because it's very fast, we have a much poorer quality of the film compared to the low pressure CVD, which is much slower. The third one is called an atomic layer deposition, and it's used to deposit very, very thin layers of a single atom layers. So we don't use it to make a very thick layers. We use it when we need the very thin layers of single or multiple or a couple of atoms thick layers. And it be done by layer deposition in cycles. So the first part is that we introduce a pulse of a gas and we have a layer. Then we remove this layer, we purge it out, and we put another gas, another cycle, and we get another cycle of a gas. And then we remove, and then it returns and we have another layer of another layer, and another. So that's be done. So the thickness, the number of layers, it depends on the number of cycles that you perform the ALD, atomic layer deposition. There are also types of electrochemical deposition, also a chemical reaction. It's related to electrochemistry that we learned about. So for example, if we have some kind of ions, metal ions on the electrode, we can have an electrolytic cell, apply current, and cause for the metal ions to be reduced on the surface of the electrode, causing a thin layer of the material, of the metal. These kind of reactions can go very slowly or very fast, depends on the current density that you use, which can provide either a very uniform coating, very good quality coating, or a very poor coating if you want thicker films. Okay, so we talked about physical or chemical deposition. Do you have any questions on this kind of additive techniques, or specifically the chemical vapor deposition? No questions? Okay. So we had the wafer, we had the photoresist. Just a second, let me draw it. So we have a substrate, and we had the photoresist on both sides. We learned how to, let's say, evaporate a metal layer, gold layer on top of it. And now we need to learn, okay, how to remove some of the material. These are the subtractive ways. And for that, it's called etching. And you can use either wet etching or dry etching. Wet is using a solution, dry, it's without a solution, to remove the material that we want from the substrate. So like we saw the conformal and the uniform coating, we also has a kind of parameter that tells us how good or how was the etching process. We have isotropic etching versus anisotropic etching. And the etching is based, it's actually calculating the, so where is it? Yeah, it's basically comparing between isotropic when we have the same rate of etching is similar, either horizontally or vertically. Or for anisotropic, it's when the rate is different, when we have a faster rate towards horizontally than vertically, for example. And usually it depends on the technique that we use. And also, for example, for anisotropic, it also depends on the, for example, for silicon wafers, on the crystallinic plane of the silicon, if it's 111 or 100 and so forth. And how do we calculate it? We calculate the anisotropy, which is A, the degree of anisotropy. And for that, we look on how much it was etched towards this direction, and how much it was etched towards this direction. So vertically, horizontally, we have U and D. And for that, we can calculate U over T, which is how much distance it went, right? Its velocity, its direct path over time, its velocity, over, this is the lateral etch rate, over the vertical etch rate, and minus will give us the A, the degree of anisotropy. Meaning that if we have a similar etching rate, this one equal to this one, so it's 1/1, 1 minus 1 is 0, so we have A equals 0, so we don't have any anisotropy. Anisotropy. We have basically isotropic etching because the rate is similar towards lateral and vertical. However, when we have much faster, here for example, much faster rate etching towards the vertical direction, so what we have is that this value is very, very small than this value. Okay, so this number is almost 0. So we get anisotropy equals 1, meaning that we did have an anisotropic etching. Any questions on isotropic and anisotropic etching? Okay. So we have two different types of etching. We have the wet etching, which depends on what we want to etch. We are choosing the etchant, the aqueous solution that will etch through chemical reaction. For example, if we have silicon oxide, SiO2, we are putting an etchant solution called HF that has an etching rate of silicon oxide of about 2,300 nanometer per minute because of this chemical reaction. Sorry, because this chemical reaction with the HF together with silicon oxide. Or we can put the silicon oxide in the presence of vapors, plasma vapor of CHF3, that will also cause, and oxygen will also cause etching just without the solution. So it's a dry etchant with this kind of rate. So depending on what we want to etch, we are choosing either wet or dry etchant. For example, for gold, for the electrode, we are usually using Ki plus iodine 2, and you have an etch rate of about 660 nanometer per minute. We put in solution. So depending on the thickness, we know how much thick gold we put, right? Because of the time that we did the evaporation, you know what is the thickness, and for that we can calculate how much time to put to etch the gold. Such, for example, we are coating with 300 nanometer thick gold. So if we want to put in solutions, so usually we put less than 30 seconds to etch all the gold. Okay, questions so far? So this is an example of a wet etching. We have anisotropic etching through the material. Depends on the time. You can have different trenches. Sorry. Dry etching, using vapor or plasma to remove the material. It can be either physical etching, just by bombarding with ions and removing the material, or could be reactive etching by chemical reaction, also by photodissociation by using photons energy. And many dry etching, they actually cause anisotropic etching profiles because they are coherent from one direction, usually from the top. So one example of one machine that does it for dry etching is ion beam etching or ion milling. And what does it do? It's kind of like milling. So you apply a very strong field that causes ions from plasma to heat the substrate. And whenever they heat, they just, mill it. They just remove the material where they hit. So it's a physical, it's not selective to any material, just hit the material and remove it. However, we have the reactive ion etching, RIE, and here it's indeed based on a chemical reaction. When you have the plasma of molecules, they react with the substrate, causing a reaction that causes the material to come into a gas phase and be removed. So slowly, the plasma ions interact chemically with the substrate, causing them to be removed. For example, silicon. We have a substrate of silicon. It's solid. We put the gas of SF6. The gas is in a plasma condition and interacts with the silicon, causing SiF4 plus SF4, both are in gas. So the gas is just flowing outside of the chamber. So RIE process is used to etch different types of substrates, mainly for silicon, where gradually, due to the chemical reaction, you remove the substrate. There's also the deep RIE, and the deep RIE, it's kind of similar to reactive ion etching based on a chemical reaction. However, we can get a much thicker trenches. And the process is that you flow the gas, and which has a much faster etching rate towards the vertical direction. And then you flow and you deposit a polymer on the top of the trench, and then you apply again the gas. And because the etch rate is much faster towards this direction, it will remove the polymer much faster than on the sides. So it will continue to etch here, while in the meantime, it didn't etch to the lateral area. So this is kind of like repeats of a deep reactive ion etching, usually have a much longer or deeper trenches if you want to etch your substrate. This is how it looks, very, very beautiful. You can make very nicely aligned, thick structures with the deep reactive ion, and very nice, very smooth surfaces. Okay, any questions so far on deep reactive ion etching, ion milling, dry or wet etching? Any questions? Okay, so I know that I'm running kind of fast, but the thing is that you need to take from here is that there are different techniques and nobody knows all the techniques. I don't know the techniques. I know specific techniques, how they work, what is the physics, what is the working principle is, and then I learn how to use them and to build my device. So nobody needs to know all techniques, but you need to be aware of other techniques that you can use as tools for you to make your device. Okay, so wet etching versus dry etching. Wet etching, usually it's a chemical reaction, right? We put in solution, has a low resolution, it's a low cost. You actually can reuse the solution to etch other cycles. It's very hard to control direction, so usually we have isotropic etchings, and usually very, very slow. So it's about 1 to 10 seconds per minute. No, it's 1 to 10 tens microns of layers per minute. So it's very fast. On the contrary, there is the dry etching. For example, the reactive ion etching has a very high resolution because you can align a very strict beam of ions where you want to have the reaction. High cost, you need a very high energy for that and gases, and has a very deposition, has a bit slower deposition rate or etching rate than the wet etch. So here's an example, case study of fabricating a single nanopore for DNA detection, and here kind of coming back to the lab on a chip, and these guys wanted to make a DNA detection. And how does it work? You have a pore that it's big enough, a diameter of 5 to 100 nanometer, and the DNA can flow through this hole to the bottom chamber. And when it flows, you measure a signal. You see, you have 2 electrodes here and here, and you measure changes in the electromagnetic field. So you measure changes with the signal. Here it looks much better. You have 2 electrodes, nickel, and just the DNA flows through one side to another. And the idea is that whenever the DNA flows, so you get a signal. So to detect how much DNA copies you have, for example. So how did they make this kind of 1D nanofluidic element of very, very thin size of a nanopore? So they did it by using ion beam lithography, etching. So ion beam etching. And because it's a very fast reaction, they're able to have a very controlled beam of ions. It's a physical etching, right? Dry physical etching to continuously mill or etch this kind of area of the pore until it reached to the other side. So it required 100 micron thick layer to go through and to etch it. So this is an example that when you need a single nanopore, you can actually have, using the ion beam milling, just to go through a layer of PMMA, of a resist, and to get into the other side. Any questions on this slide? Now, to choose which kind of etching is the best way is to look at recipes of other colleagues or some kind of experience, which kind of recipe to use, or if you've seen papers. And if not, you can choose your own recipe and then try to optimize it, see if it works. If not, change some parameters, and you can try trial and error until you get your process correctly. Now, how we can utilize this kind of microfabrication, not only to make, for example, electrodes, but also for microfluidic lab on chip. And for that, it's kind of a similar way. It's kind of a way that we use a mold or a stamp. The first part is to use photolithography to make our mold. And then the second part, after you do photolithography, you make your mold, you pour on top of it a polymeric substance that when it cures, you can remove it and make the channel. So this is an example of how you actually do photolithography. So the first part is making or fabricating. You have a substrate with a photoresist layer here. Now, instead of putting gold, because it's for electrodes, we are leaving the photoresist here as kind of like a hump. And then we pour all the photoresist on top of it. Sorry, all the PDMS, polydimethylsiloxane, all this material. It's kind of like a polymer. You put it and then you put in the oven. You cure it, it solidifies, it becomes solid or a bit rubbery, like this kind of rubbery. And then when you remove it, you have this kind of structure, right, of the polymer. And this structure you take and you bond to, for example, a glass substrate. So the flow or the channel that is being developed is actually happening here. This is where the flow will go inside and to the other way. So the first part is to make the mold using photolithography with mask and photoresist. But instead of doing the features of, for example, gold electrode, we leave the photoresist as the negative structure for our channel. We pour, it's called soft lithography. So we pour polydimethylsiloxane, PDMS, PDMS, and we put it in the oven, let it cure, be solidified, and then we just peel it off and stick it to a glass, making the channel direct, making the channel structure. Okay, any questions on soft lithography or how to make photoresist? How to make channels?
The PDMS just connects with glass directly without any other materials?
It's a very good question. PDMS, if it's bind automatically, so usually it binds, has some kind of connection, which is good for most microfluidic applications. However, in some cases, you can have kind of a treatment with oxygen plasma, for example, that will open the connections both on the glass and the silicones, chemical connections, and when you put them together, you're going to have a much stronger bond. So it depends on the application, but you usually you can do another process that have a better bond to prevent, for example, leakage between the glass and the PDMS.
Oh, I see. Thank you.
In my lab, we have a plasma oven that we are flowing oxygen in and we make a plasma in order to make the bonding much stronger.
Thank you.
Thank you. Any more questions? Okay. So if you want to summarize what we have learned here, we've learned different ways or different techniques, not all of them, but different techniques to fabricate structures and different resolution, different sizes. For example, if we wanted to fabricate 50 nanometer thick needles, such as we have a substrate and we have needles like this, in order to, for example, to introduce some kind of solution to that, the needles will go through the skin, and we're able to to interact with the solution or the fluid underneath the skin, which called the interstitial fluid, ISF. So this kind of work, and the way to do that is that we look for the 50. Sorry, here, and I guess we could use ion beam lithography or single point e-beam, electron beam lithography, when we pour everything with a resist that responds to electrons, and we have a very, very thin, coherent beam of electrons. Any questions? Okay. So here I'm going to finish the lecture number 8, and we talked about different techniques for micro nanofabrication techniques. We learned about the process, how we choosing the substrate, how we put the photoresist, we do the photolithography or the e-beam lithography or any kind of lithography, patterning those structures on the substrate. Then how we can have different ways of material additive techniques to put the gold, for example, or other materials, and then how we can subtract or remove specific areas of the material to manufacture and to make our device how we would like it to be. So it's kind of really a process, a manufacturing process that you optimize, to build and optimize and develop. And eventually you can do that continuously, repeatedly, and get the same results. Any questions on this lecture? Or any kind of fabrication or lab-on-chip devices? Okay. So here I'm finishing the lecture, or basically the class. This is the last session of the class. Hopefully next year I can also teach the class, hopefully in person, and come to China. We started with some kind of a high level, system level of what is biomems, what is lab-on-a-chip, what kind of components it built on, how to connect it with microfluidics. Then we went down into the molecular level, trying to understand what are the physical-chemical processes, reactions happening at the molecular level, how they can be utilized into electrochemical detection in electrochemistry, how we can design and simulate a lab-on-a-chip, what are the guidelines, and eventually, after we design them and we know that we want to make this kind of lab-on-a-chip for our experiments, we are going to the clean room and fabricating the device. So here I'm finishing the class, and if you remember, we began with Thomas Wheeler back in the Middle Ages that tasted urine to diagnose diabetes and said it was wonderfully sweet, as if it were imbued with honey or sugar. So I hope I convinced you that the field of lab-on-a-chip device of biosensors is going there and able to show new solutions, new miniaturized and small microscale and nanoscale solutions to translate or to provide medical diagnostic information. And this is the future, and based on you guys, you are the future scientists, future future researchers, to think about or invent new ways to diagnose our body. So that was the goal of this lecture, of this class. And we learned about different directions. It was kind of in the high level, but I hope you also will be intrigued in the more practical level to learn more about this kind of area. And I very much enjoyed teaching you, and thank you for everyone that asked questions. I really enjoyed it. And I want to finish with that to say that if any one of you interested to learn more about it, we actually have an open position. We are for excellent students to come from China to Israel. We have also very nice scholarships for that. And feel free to contact me on any kind of subject on this approach. So thank you, everyone. Be safe. And that's it. Bye-bye.
Thank you for your class.
Thank you very much. Sorry.